Hello and welcome to Rudy's Electronics Lab. Today I want to talk a bit about the new frequency counter that I purchased, an Agilent, to replace an older counter that had a quite limited resolution and other limitations. And I was quite excited about getting this new counter, a 12-digit counter, but even more excited when I was playing with the device and actually learned that it should be able to produce as much as 15 digits, an incredible amount of resolution. So the main themes of today's episode are going to be how do we get actually these 15 digits out of the device, because actually you cannot see it on its own display. But the second and also at least as important theme, does it make any sense to have that wish to have 15 digit? Are these really useful type of information, etc.? Or is this just insignificant type of rubbish, and should we not desire that type of things? So what can you expect in the episode? First, I'll talk about the limits of my existing 8-digit frequency counter and about how I ended up selecting this Agilent counter as a replacement. I want to talk a little bit about the theory and especially going into the question of the relationship between the number of digits that we see and gate time and also time-based encounters. Then we actually go and do some measurement and testing ourselves, and we're going to try to see how we can get the 15 digits out of the device. And then we end by a discussion of errors in frequency counters, trying to understand, does it make any sense to want like 13, 14 or 15 digits out of this particular device? And then I'll end up with also some more general observations about having used this device now for a couple of days in the lab. So off we go. Now my existing frequency counter, it's the I'm using right now the Agilent SDZ series of it's actually a signal generator. It's not really a counter, so it's not completely fair basically to judge this only on its counting capabilities. But anyway, it has been a bit limited, this functionality for me until now. As a counter, it's only shown up to 8 digits. So depending on what we're measuring, so suppose, and we're going to talk about this episode a lot about measuring and especially comparing frequencies around 10 megahertz, depending if we're just below 10 megahertz or above 10 megahertz, we're going to see a resolution of 0.1 hertz or a full hertz basically. I was also having some doubts about the way that the mean was being calculated by the Agilent counter, and I'll show a little bit more when we go to the measurements over here. But anyway, I had a bit of a desire to have a counter with a higher resolution and accuracy. And maybe I should also kind of stress that I'm particularly interested in comparing frequencies. So less so in the absolute measurement, that also requires a very accurate time base, but especially in comparing them or comparing from an external time base, like a GPS discipline type of oscillator, like the Leo Bodnars that I discussed recently in my episodes. Now, looking at the market for frequency counters, there is not terribly much on the market. I mean, standalone frequency counters are a little bit, becoming a more and more odd type of product there. And if we look what is currently available on the market, you would have, for example, more affordable models of the AIM-TTI TF9 series. You see it here on top. The current Keysight models, I wonder even if they're still current or maybe being phased out as a product by themselves. And for example, the Tektronix FCA 3000 family of devices. These are all manufacturers that make multiple type of product. They're also kind of specialist companies that are completely focused on making high-end type of frequency counters. And I was looking a little bit at the market. I came across, for example, this instrument of a brand called Pendulum. I didn't know them in advance, but they make several families of devices. In particular, this CNT100 family looks like very exciting instrument. It is available with very precise rubidium clocks inside that actually are also satellite disciplined. And the use case that they're talking about themselves is, for example, a phase comparison of 4 atomic clocks. So that's pretty exciting. And also, if you look at the manual of the device and you see all this user interface, it really looks very impressive. But I'm certainly not going to buy this. These are very expensive instrument. So let's then take a look a little bit at the specification of different type of counters on the market and how they line up in terms of both specification and price. Now, in this table, you see the various devices, and their base measurement frequency is usually between 200 and 300 or 400 megahertz or so. The exception being here the AIM-TTI is a little bit the odd one out. It has a 3 gigahertz base frequency, or standard it supports 3 gigahertz, it's not optional, but I think it's using a pre-scaler to do that, in contrast to the rest of the devices that are kind of regular counters on their base measurement frequency and have pre-scalers when they go to optional higher inputs, and then these models basically go until 6, 20, 24 gigahertz or whatever. We can also then look at the number of digits that are shown on the device. Again, the signal, not a real frequency counter, but as a point of comparison, it can show a maximum of 8 digits. That was my limitation using the device. And the frequency resolution in terms of how quickly it can calculate a result with this amount of digits here. It's not in the specification like all the other data on the sheet, but I measured it as about 1.5 seconds to resolve 8 digits of data. The AIM-TTI is a device that can show 10 digits, but oddly enough, its speed to resolve these digits is relatively low. It can only resolve 8 digits in a second, or 9 digits in 10 seconds, or 100 digits in 100 seconds. So it needs 100 seconds to show the number of digits that are kind of standard on the display of the device. That was not very impressive, if you would ask me. Then the much better devices basically are the Tektronix, the Keysight 53000 series, and this pendulum device. We see here, these are devices that can show up to 12 digits. I think the pendulum even 13 digits, I wasn't completely sure. They can resolve that pretty fast, like in the range of 12 digits per second or so. And if we look into the further specification, and in particular we see that the more expensive the device is, the better the specs also are in terms of time resolution. And time resolution is the smallest measurable time difference between two events in a single shot. So in other words, ability to determine very precisely when something happened in time and with what granularity or specificity. So the very, very good counters would also have like a very small time resolution. You see it on this sheet. Actually, I don't have that data for the AIM-TTI or the Agilent. And then finally, of course, relevant is the price. And well, the Agilent is a couple of €100 device. So is the AIM-TTI. But when we go to the Tektronix, the Keysight, and the pendulum here, we talk about 4-digit, even 5-digit prices. And even though I really like to have a nice frequency counter, I was kind of not willing to spend that amount of money on it. So enter the device that I finally decided to buy, a Keysight Agilent counter. Basically, that is a second-hand model that is doing pretty well in terms of specification. It's a 12-digit device. It can resolve 12 digits per second. It got a very reasonable time resolution, and price-wise, the devices, there's quite a lot of offer on eBay. I think quite a lot were produced and sold, and the price is vary a little bit, but I got it for a couple of €100, and I'm very happy with this purchase. And now with the Keysight, so we got 12-digit resolution with a 1 second gate time. So let's dig a little bit deeper into what this device can do for us. So the one that I bought on the market on eBay basically turned out to have the latest firmware revision. Actually, earlier firmware revisions are a little bit more limited in their functionality. Also, serial numbers that are kind of below 4,000 or whatever, it's kind of the same story. I'm not sure you can actually update just the firmware device. There might be hardware differences as well. But anyway, this is the latest version. I got the 3 gigahertz frequency option installed in the device. That is quite nice. So you get like a third channel. There is something odd, by the way, by the device, the example that I bought, and that is that the device has a kind of a warranty calibration kind of sticker on the bottom of it, as if the device was not opened. But if I look at it, I'm pretty convinced that actually this 3 gigahertz option is not the original Agilent one, but it's an aftermarket one that was installed pretty recently. Maybe you can also see, if you look at the picture shown here, that the third channel looks like very shiny connector, etc. While the other channels, you can already see they're like 20 years older or so. I'm pretty sure that this has been added much more recently. I don't see why they had then to put this sticker on the device and kind of suggest that this was an original configuration or so. I mean, just leave the sticker off, I mean, and just be transparent that it's a later option. I've been measuring it. I've been measuring the sensitivity, for example, of the input channels, including the 3 gigahertz third channel, and they all comply to the specifications perfectly. So there's nothing to be unhappy about this 3 gigahertz option here. I just find it a bit strange that they seem to be fooling you with this sticker, but so it be. I got the standard time base. Optionally, you also have like the medium stability oven, the high stability oven, or the ultra high stability oven. I don't have that. To be honest, I don't really care so much about it, because that also kind of means that you have to leave the device running 24 hours a day, 7 days a week. Keeps it on temperature, keeps the ventilator running, is making noise, is consuming a lot of energy. I'm going to use an external GPS disciplined oscillator anyway, the Leo Bodnar, so I don't care too much about that. Even though it is kind of cool that if you got one of these optional ovens, it got an automatic calibration procedure for them, while for the oven in here, the standard time base, you can calibrate it, but you have to do it with a potentiometer, and it's not so sophisticated. Yeah, and then finally, as you already see on the picture showing here on the screen, the device has a 15-digit settings here. So that's what I'm going to focus on right now in the video. Now, what would it mean if we're able to get as many as 15 digits here? Now, I'm going to try to put that here in a little table. So if we have a reading of 7 digits, and suppose that we're measuring exactly 10 megahertz of frequency, it would basically mean that we got a resolution in our reading of 10 hertz, and relative to 10 megahertz, that is a resolution of one part out of a million, 1 ppm. So we're talking about 10 minus 6 here. Then we can add the number of digits, and then of course basically our resolution goes up. So we can go to 0.1 ppm, 1 hertz resolution. This is all relative basically to the 10 megahertz. And when we further go down, we basically go into the range where we're talking about parts per million, then to parts per trillion, etc. And we could go all the way down to 15 digits here, as I show it here, for a 10 megahertz signal. Actually, this is assuming that we're measuring 10 megahertz, so the first digit is a 1. Actually, if we're measuring just below 10 megahertz, so 9.999, we got, with the same amount of digital resolution, of course, we get a frequency measure 1 lower in frequency. Oh, let me just show it. This is hard to explain, but we see the 9.999.99 if we only have 6 digits there. And basically then, if we go all the way down to 15 digits, if that were possible, we're not only getting in the part per trillion, but even in the parts per quadrillion. That's crazy, right? So it's a 10 to the power of minus 15 or so. And theoretically, my signal should be then at the 10 minus 8 type of range. The new Agilent would be in the 10 minus 15 range. That would be very exciting, but well, this is in theory. Does it actually work, and does it actually make any sense? I'm going to try to further answer these questions in my video. Now, how do you basically determine the number of digits that are measured by the device? That can be done basically in 2 different ways. And both of them are basically the arming settings for the device. So by default, it is on automatic arming, and then you get 12 digits. You can also go to external signal arming. You connect an external input, and that basically starts the arming of the device. But there's also 2 modes which are called timed arming and digit arming, and they allow you to go all the way up to 13, 14, and 15 digits. And in the timed arming, basically you set up your gate time, which can be like a second, 10 seconds, and can go all the way up to 1,000 seconds. And the longer gate time you choose, at some point you get an additional digit out of the device. When you're using contrast the digit arming, you basically select as user how many digits you want to calculate, and then the device should choose the gate time that corresponds with that. Now the strange thing is, and I don't have an answer to that, if I do digit armings, it takes a lot of time. If I select 12 digits in just 12 digits, like the regular automatic mode in digit arming, it's already taking like 10 seconds to resolve them, and then it goes up to incredibly long time. However, if I go to time arming, I get that same amount of digit actually in much, much shorter times. I really don't know exactly why that is. That seems to be no different in terms of accuracy of the measurement. Actually, in all the detailed specifications of the device in terms of error you can expect, actually they kind of mention the time arming and digit arming together as a category, whereas basically the accuracy for the automatic modes is different. So I'm not really getting that, but we'll show a little bit more about that when we're going to do our measurement experiments. Now, as you saw in the previous sheet, there is already a relationship basically to gate time and the number of digits that we're getting. And to understand that a little bit better, I want to go a bit into the inner workings of frequency counters, and I'll start talking about what we will probably call something like a conventional frequency counter and how it works. And this will be a very simplified type of block diagram. So in this example, we got like a signal coming in that we want to measure. And in this example, it's a 2.5 Hertz signal, basically. And we're going to measure that by basically using a gate that opens and that closes. And we're going to see how many cycles of our input signals basically are passing by the time that gate is on. And that gate basically is open and closed by a very precise internal time base, and there's going to be dividers there. And in my example, I'm going to take a gate of 1 second. So the gate is going to open, it's going to count the number of pulses coming in, and after exactly 1 second, the gate should close again. And then we basically should know, counting the number of cycles there, what is the frequency of the input signal. But there's a limitation basically that has to do with quantization of the input signal. And let me try to show it there. And again, we're starting with this 2.5 Hertz signal and this 1 second gate, because then we can really easily see where the issue is. Now suppose that the 1 second gate opening is represented here in this picture. We open the gate and then we actually see 2 pulses coming in, pulse 1 and 2, before the gate closes again. So our frequency counter would conclude that we got a 2 Hertz signal here that we're measuring. Actually, it is 2.5 Hertz, but the counter would basically say it's 2 Hertz. Now, if I would measure it again, and actually the gate time would be a little bit differently situated vis-a-vis the income time, but still be exactly 1 second here, then actually the gate would open and it would observe 3 counts before it closes again. So the timer would think it is a 3 Hertz signal. So depending on the exact timing basically of the time base versus the incoming signal, there's an inaccuracy basically going on there, and I'm exaggerating here by choosing the 2.5 Hertz signal, but this is basically already telling us if we're measuring this way, basically we're going to be very limited in resolution, because the last digit basically is going to be an uncertain digit that will be jumping between 2 and 3, and we don't know exactly which of the two it is. Or it might show 2, but in reality it might be 3, etc. Yeah. Of course, if we're measuring a much higher frequency signal, if we measure like a 100 megahertz signal, there are many more counts there, and then the inaccuracy the resolution is much higher. But this is going to be a systematic limitation that we're going to have here. There have been some ways to counter that. For example, in some counters there's synchronized gating, where the gate only opens at the moment that an incoming pulse comes in, for example, and then you solve half of the problem. You solve the quantization at the start side, but not yet at the stop side. Now there are also other types of counter design. So the counter design I just talked about is the conventional frequency counter, counts the number of signal cycles in a fixed gate time. So if we now assume for a moment a 100 Hertz signal, if we would take a 1 second of gate time, then our measurement would show 100 Hertz plus or minus 1 Hertz because of that uncertainty. So there will be a 3-digit outcome. Yeah. So the resolution is 1 Hertz for 1 second of gate time. All right. Another type of counter would be the conventional period counter. I'm still talking of counters that might have been made 40 years ago or so. Actually, it does exactly the opposite thing. So basically, then the signal to be measured, that is being used as the gate signal. And while that gate signal is there, we're basically counting the number of pulses coming from the time base. So we're actually turning around the way that the gating works in this device. So we determine the time for one single cycle to complete its thing to do. And if we do that, basically, we get a much higher resolution, basically, if we're still measuring that same 100 Hertz signal. So taking a 100 Hertz signal and assuming that we're using a 10 megahertz time base, basically the device would show us 10,000.0 microseconds plus or minus an uncertainty of 1 microsecond. So we get a 6-digit display. So frequency counters are good at relatively high frequency, measuring relatively high frequencies. Period counters are good at measuring relatively low frequencies. And actually, if you calculate out, and this is taken from an example from Agilent manuals, then we can actually see that trade-off between the two of them. These days it's common basically to use a so-called reciprocal frequency counter. And what it does basically that it can measure the period, and because 1 over the period is equal to the frequency, we can just show it as a frequency. There was an issue in the far past, but nowadays, of course, with microprocessors, we can simply calculate from the one value to the other value. And that is also the way that the counter works that we're looking at today. I think it actually switches between frequency counting and period counting depending on where you are in the range. But the bottom line conclusion is that the resolution, so the least significant distance shows, varies with gate time or time base. And you can increase the gate time to get better measurement at the expense of having to be very patient perhaps, or you can increase the time base in the case of period counters, but that requires basically a more expensive implementation in the device. At some point when I was preparing this episode, I also asked for the help of ChatGPT to show me how many digits exactly the new Agilent could show as a result of gate time. Actually, when I was looking up some stuff, ChatGPT was suggesting that he could do that for me. So he created a bit of code specifically for this type of Agilent counter here. And here you see the results, and they're like total bullshit. They don't even go to 12-digit resolution, or they only go to 10-bit resolution. I don't know what to do, but it reminds us again not to rely too much on this type of stuff like ChatGPT if you want to do stuff. You can find some interesting stuff that you wouldn't have found otherwise, but let's be very critical about its output. So let's forget about it. And as a matter of fact, Keysight Agilent already provides us with very excellent documentation on these devices, which I think are a much more reliable source. And when I talk about very much, then I mean really we got this whole bunch of information. This is not everything that I got printed out, but we got a manual of some 200 pages that is very detailed. We got a programming guide. We got service level service guides. We got components level device, and we also got all types of application notes that are very useful. Fundamental of frequency counter, fundamentals of what we got the time interval measurement, hints for making accurate measurements, like the whole stuff. It's worth reading this if you really want to understand your frequency meter well. And especially the document, which is the component level information, is as detailed as you would really like it to be as an engineer. Yes, we get the full schematics here. Here you get to see the two input signals. You get to see the logic part. You basically get to see the full schematics for the 3 gigahertz and the higher option that are there. So here we see the prescaler basically. And before the prescaler itself, we see basically a range of cascaded amplifiers there. So yeah, perfect type of information being available here. We are now in the lab trying to do some experiments. We got the Agilent here, we got our Siglent, which also has a frequency counter in here. And I put a little screen here as I can record it a little bit easy here. And actually we see on the screen, we see the Leo Bodnar GPS disciplined oscillator, and that is actually providing a reference signal to both of the devices here, and it's also providing a measurement signal which is 12.3456778 megahertz here. So that will be our testing signal. And basically the Agilent here has dutifully been trying to collect that information. So we already got like 5,000 measurements showing here with all the statistics, but they can only show it so basically at 8 digits level. And also the degree to which the mean is jumping up and down over that many measurements, that doesn't give me a terrible amount of confidence. So we're going to look at how the Agilent meter is doing. So let's start up the Agilent right now. And one thing I really like about it is that how crazily fast it starts up. It's just going to show you, it's self-testing the general purpose instrument bus interface, and that's we already got it running here. This is the default setup settings. There are some program settings like the GPIB identity number and a couple of other things, but we don't really need to look into that right now. We can see that it's showing basically 12 digits on the screen right now, and it has a short gate time. I believe that is 1/10 of a second. So 10 times a second it is able now to collect a 12-digit measurement on the screen. And we're going to try to see how we can get additional digits out of the device, because that is not going to be that easy, at least not on the device itself. But let's get there. First of all, before we try to do any measurement that might be long or so, we're going to take care of two things. First of all, we're going to lock the device into having an external frequency reference. By default or factory, I think it's set on automatic, but in the manual it explains that that might actually delay your measurements a little bit. So I've basically already programmed it basically to be always looking at the external reference. And the other thing I will be doing basically is going to the channel settings and basically not use automatic triggering. Now this is a very simple signal I got coming in here, so it will be doing perfectly fine measuring that. But when it's on automatic triggering, basically it has to determine the 10% point in your waveform, the 80 or 90%, the 50% in between them to find its trigger point. That can all take time, and we don't want all of that, so we're forcing it basically in this mode here. Now basically what I want to do here is set the device to a different number of digits. And we can basically do that by going to the arm, the gate and the arm button. And right now it's gating on time. You can also have like automatic gating going on, but I want to gate it external gating with the external port, but I want to gate it on the number of digits. And here we can basically see that right now we're gating it on 4 digits. So if I choose 4, and I do single stop, he's doing a single measurement here, we'll see 4 values. That's exactly how we would have expected it. Let's set it to a higher number of digits. Let's set it to 8 digits. And we get to see 8 digits, well, everything like expected. If we set it to 10 digits, it really takes a little bit of time, like 2 or 3 seconds. And I'm quite surprised, because earlier we saw it basically doing 12 digits at a very, very high rate. And now already having like, like 10 digits was already getting a little bit slower. If I do 11 digits, and I'm going to actually using my, my stopwatch here. Nine seconds. For 11 digits, and I'm not going to bore you with it, but I can already tell you if I choose 12 digits here basically, then I have to wait for 40 seconds. So that's really a big question I have. Why does it take 40 seconds to make a 12-digit measurement in this way, while if I leave it basically on the time mode, the gate manually set, etc., I can actually get 12-digit measurement more than 10 of these per second or so. I have no clue. According to the manual, these modes are rather similar, opposed to the auto mode, and the measurement precision is the same over these modes and everything. So I really got no clue here. But what I will be doing basically is using this device basically in the time setting mode, where I'm actually not in the auto mode, in the time mode, where actually I will be able to choose my my own gate time. And for now, let me just start with a gate time of 1 second and take one single measurement. So every time it opens the gate for 1 second, basically, if I do stop single button, single means that I do one single measurement, run means that it's going to do continuous measurement. Now, if I want to get the additional bits out of the machine, I have to connect up a computer, and already have been setting this up a little bit, and here we basically got like the Keysight I/O manager, or more specifically the interactive I/O module of that. And that allows me to talk via the general purpose instrument bus, the GPIB, using Skippy commands to the device. So basically, if I go here, and let me see if my setup is correct, if I ask for the identity is star IDN question mark. Did I make a typo? Yes, I did make a typo. That's what I felt. And I get it to report back, it's Hewlett Packard, and then the type number and the revision number. So my communication is running well. And in this mode, basically, I'm also able to basically fetch a number. Oh, I'm getting the identity again. Let me see here. Frequency, fetch. And I'm basically getting the value out of here. So here I'm getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits as expected. Here I'm getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 digits already. So basically I'm getting more digits already when I use a longer gate time and when I consult it via a computer. So let me increase the gate even a little bit more. Oh, I'm in remote mode, I have to remove it of remote mode. Let me take a 10 seconds gate and run a single measurement. Okay, 10 seconds are over. Let me get the value, and as you can see here, we're actually getting an additional digit here to the interface. So now I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 digits. So that's what I'm getting basically to 15 digits on the machine. But doing that, you need the GPIB interface bus, and to do that you need a quite expensive adapter. I'm basically using here this, let me show it to you, this Agilent Keysight 82357B adapter, and I think it's got a retail price of something like over €1,000, although you can get them cheaper. But I'm showing you this because there's actually a much cheaper way to do this little experiment that I'm doing with you here today that doesn't require that expensive adapter at all, and is actually more attractive, I would say. And what is that basically? Now let me get you to another little program that I prepared over here. There we go. As you already can see, we're actually going to use the serial bus of the device. It got a serial bus like an RS232 bus, and that is can show all the measurement value. It's a talk only bus, so you cannot program it, you cannot send commands there, but basically you can read out the internal values. In order to configure that bus, what you do is basically turn the device off and keep the recall button. Super fast, revision number, and we get here all the settings here. The baud rate, which is also the bit rate, because there's one symbol at any point in time. Parity. There's also the DTS settings. I don't know why it's called DTR here. And that's quite interesting because it doesn't only have the regular value hardware handshaking, but also limit. But there's another time I think I'm going to talk about that. Well, and all the settings are here of the serial bus. So with the serial bus being properly configured, turning on the device again. And I'm going to try to get it, sending its measurement values basically over to the serial bus over here. We're not seeing anything yet, but we need basically the save and print button for that. Go to the right value in the menu, on, and well, there we already got it. All the measurement values basically are being sent over, so it's a bit easier basically to use the single mode, and every time I press it, I'm going to get one single value here. So this is basically very practical. So if I now choose again a longer gate time, and let me try to get to these, let's get to the 5 seconds of gate time. I get 5 and 1 millisecond. 1, 2, 3, you see the gate symbol, 4, 5, basically, and we get here, and we indeed get also the higher resolution, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, with 5 seconds of gate time, and if I increase the gate time further, I also get like the 15th digit here. Now, there's also another reason why I'm pretty excited about using this serial interface. And let me show that to you, because it's very nicely integrated with the statistics settings of the machine. So let me go to statistics. Let's say that we want the standard deviation. Up, there we go. Furthermore, we choose the end of the statistics. Now let's take 5 for the time being here. We're going to use all measurements. We can also tell him basically to use only the measurements that are within the limits, the upper and the lower limits that are set for the machine. So you can discard like extreme outlier type of things. I'm not interested in that. But what I'm interested in is in this setting, on single 1. So what does that happen? Normally the machine, if you press a single button, it will take one single measurement. However, if you put the on single on n, it basically means that it executes all the n measurements in one go that are required for the statistics, and then we'll stop again. So a single burst of n measurements. So I'm good at it right now, and I think the device is still set to a 5-second gate time. So let me basically clean up the little screen here and let's run it. Now we've got a 5-second gate time. We see that the gate is being opened, and we're going to repeat that for 5 times. And every time we got results, actually we already show it on the screen here. We're not seeing it yet on the device, just telling us that it's doing the statistics on its values, but you get to see the intermediate values here every 5 seconds. The nice thing is actually when the 5th value comes in, and there it is, very nice. Not only the 5th value, but we get to see the standard deviation. That's also what we see here on the machine. We get the mean, the max, and the minimum. And in this case, actually, we also get a additional digit for showing the mean, because you can do it on more measurement values. So this is a super practical way in getting not only, you know, the long digit type of measurement out of the machine in a very cost-effective way, but also to do the statistics nicely on it. And so you don't need this expensive GPIB interface, but you can just be using like a simple serial bus. And if your computer these days doesn't have a serial bus anymore, what I'm using here basically is this little DeLock thing here, an adapter from serial to USB-C. I mean, they cost 20 euros or so, I think. And then you get all the functionality basically out of the machine. Now, while the video camera was off, I did basically a larger run of measurement values, and I did 10 times a measurement of 100 seconds of gate time. Actually, you can also do 1000 seconds of gate time, and I will limit myself to 100 seconds of gate time. And so after having all these measurements, I'm getting a standard deviation of 0.6 microhertz, so it's over here, and all the values like being pretty close together, and also the resulting end values, and all of this basically in 15-digit presentation here. So it works perfectly fine in terms of at least getting the digits out. I really don't get it why, because yeah, this I get, you can easily go through the statistic thing, but I don't get it why there is no way basically to get the last 3 digits on the screen of the device itself. I mean, they could have used here the arrow keys or so, but they haven't. Yeah, you only get it out via a connected computer, which I found a bit of puzzling, but it is what it is with Agilent. But I'm very happy that the simple solution here, just using a serial cable, allows you to get all this information out of the machine, and in a quite nice format as well, I would say. Little funny thing to know, by the way, about this Agilent counter and many other Agilent and key size machine. There are these 4 buttons here, this pad, up, down, left and right. And in the manual they refer it basically to S, G, D and F buttons. And initially I really didn't have any clue what it is, and I kind of looked it up, and apparently it's an arbitrary but consistent naming scheme that the designer of Agilent have been introducing, maybe already back at the HP time. So they didn't want to use A, B, C, D or F1, F2, F3 for function keys, but they wanted an alternative one that should not be confused. And apparently they settled upon the letters S, G, D and F. Relatively arbitrary, but consistently over their devices, and that's how they describe it in the manual. Not super clear, but these are basically the letters. Now we get to the second theme of today's episode. Should we want this? Does it make any sense? We have to think really about the type of errors in frequency on the counter. We have to understand a little bit about accuracy and resolution. And here you see an overview of different type of errors that can occur in frequency counts as we find in the Keysight documentation. I find it quite interesting that even in the Keysight document, there are some of them that basically talk about accuracy and then resolution is a part of accuracy. There are other documents, I think, made by Keysight where they really say resolution is one thing and accuracy is a completely different thing. But anyway, I want to dig into some of the most prominent type of errors that we could have here, basically trying to understand if it makes any sense to look at the 15 digits that we were able to get out of our device with our measurement section today. So here I'm showing the picture that I also showed earlier in our episode today, and where we already learned that the least significant digit that's being displayed on the device basically varies with gate time. Now we get a little bit more into detail here, because this is a fundamental thing that any counter will basically has to deal with here. But above this fundamental thing, there's a couple of more things. And one of these things is basically trigger timing error. Because the incoming trigger signal, for a variety of reasons, might be not very precisely spaced in time, but might be subject basically to a type of a distribution. So here we take a statistical Bell type of resolution here. And that also means that basically some type of inaccuracies can come into the signal. Secondly, it might also be that we're basically dealing with a false type of triggering of the signal. Suppose, for example, that we got a signal coming in, but there is a spike occurring in that signal, and we're actually meeting our threshold earlier than we should have met it. Then we basically got a too early timing trigger coming in, which basically means an error in our measurement. Now, luckily enough, devices like this are offering us a number of possibilities to deal with that type of things, being able to set the threshold value, being able to activate, for example, low pass filters, setting the hysteresis, etc. So you can do a number of things to minimize this type of error. So error is also a matter of user intervention basically, but well, these sorts of errors do exist. The second thing that we have to consider basically is how accurate our time base is, because our measurements, at least we talk about absolute frequency measurements, can never be better than the time base we got in our device. And basically, roughly speaking, there are two types of errors. There's the long-term type of error, for example, related with aging and temperature fluctuations of the time base, and short-term stability. We can also see as a kind of phase noise, and typically the more expensive your time base, the better its performance is going to be in both of these respects. This is all for absolute measurement, where we're basically interested in comparing two frequencies. Then we don't have to care so much about the accuracy of the time base in itself. Now, how does this all kind of add up to the type of error that you can realistically expect to be present in the measurement of this device? Now, fortunately, Keysight provide a lot of details on errors, and I'm going to show some of them here basically that we find in its specifications and in the other documents. And here basically we're seeing the error, the absolute error that we can expect of the device as a function of the output frequency that we're looking at. So we see in this case for a 10 megahertz signal that we're looking at an absolute error of 10 microhertz. So that's 10 to the minus fifth. 1 microhertz would have been 10 to the minus 6. But then we can relate that, of course, to the signal itself, the signal being 10 megahertz. So basically the error in relation to the signal will be in the range of 10 to the power of 12. And basically here then we're talking about a gate time of 100 milliseconds. We're making 10 measurements a second with this type of accuracy. Now if we increase the gate time, we get a better performance, and we see that in that graph here. We go to the blue line basically, we get to the 10 minus 14th basically in relation to the signal that we're measuring. And we can even go to longer gate times. We got 10 seconds being specified here. We go towards 10 minus 15 here. And actually 10 seconds is not even the longest that you can go with this device, because you can also go to 100 and to 1000 seconds. Now the specifications don't provide this type of graph for that type of thing, but if we would speculate, then we would get lines that will probably be lying below the two lines we're already seeing. And speculating, then we're already at 10 minus 15 or so. Now we can even do more things basically to get more accurate type of measurement, because we could be basically averaging multiple type of measurements. So the standard deviation basically would decrease as a result of the number of measurements that we will be averaging here in our measurement. So if we do that, then arguably that line even goes further down. Again, this is speculation. I don't know where exactly the line would be, but it would be better than the 10 seconds gate line that we already had here. Considerably better, I would expect. So the bottom line that we're getting into, that the device can calculate up to 15 digits, which is great, when we have the right gate time, when we got enough patience, particularly when we're doing averaging, for example, and when we realize that these digits cannot be shown on the device itself, but only via a connected computer, via the general purpose instrument bus, or via the serial port, which is I think more convenient. And we have to be mindful of the various sources of error. Seeing many digits does not necessarily mean they're all accurate. Understanding these errors is key. But I think it's kind of promising what we learned today, also from the Agilent manual. And using averaging and longer gate times can even get to better results than the measurement examples that we find in the manual. But in the end, this is always going to be way better than my previous counter, and it's worth delving into beyond 12 digits of display here, if you have a use case for it. If you're comparing like two different clock sources, and that's kind of what I was looking into, yes, I think it's kind of very interesting. In terms of absolute measurements, I think your time base is going to be the limiting factor, and you should not try to go beyond 12 digits in the first place, unless you know you got like a very perfect type of time base. Let me also share with you some wider observations on the device. I've been using it now for a couple of days. So what are my impressions here? Yeah, I really love this device. I mean, look at its displays and everything. It's a top class meter. It got very good specs also for sensitivity and resolution, etc. The fact that you get the GPIB bus and the serial bus both as standard, that really helps, especially if you want to get the 15 bits out. There's a wealth of options as setting on the devices that really makes it a professional frequency meter. I'm talking about here the input channel and all the preconditioning you can do to make sure that you're triggering your signal properly, all the different type of measurement settings, the mask, the limit settings, etc. We also got a cool internal calibration. You can calibrate gain automatically, offset, electrical path differences between the channels, etc. That's all very cool. And you can also automatically calibrate your time base if you have one of the optional time base options, which I don't have on this device. But anyways, it's done in a pretty cool way. And despite the fact that it only has like one line of display, I really like the nice and logical user interface and user experience. I don't feel at all that having one single line here is is limiting. I got a lot of devices with huge screens on it and often very confusing and hard to read. This is just single line, but it just does what you want it to do. And it's easy also to read it from large type of distance. And I really love the extensive documentation, although I'll say something about that in a second as well. What are the points of improvement? That's a bit of strange to say for a meter that is already not on the market anymore. But anyway, I'm going to say it anyway. Just a small thing, but why does it have a beeper for this limits and when you would have like errors on the device or so? It's very strange. If you're using this limits type of thing, there's a tiny little thing illuminating on the display that you easily overlook. A little bit more serious, what I would really also appreciate that you would have get a little bit more insight into the gate time, especially when you're using long gate time, like 100 or 1000 seconds. It would be really nice there's a countdown timer, you know, from 1000 to 1, you see what the gate time is. That would be a very useful and easy thing to do. I like the statistics on the device. I would have appreciated if they would also added some more sophisticated stuff like Allen deviation. They did it on the next generation of models, I think the 53,000 series, but it would have been fun. I also like the mathematics, but the mathematics basically do first the scaling factor and then the offset factor. And I also would like to be able to do it just the other way around, so I can make like ppm measurement. I think some more sophisticated meters, I think I saw it on the pendulum meter, you can choose between the two of them, not on this one. And finally, if there's anything I could wish for, it would be even better documentation. Even the documentation is very detailed, I'm still left with a couple of questions, and actually I'll get to them on the last sheet here. These are things I don't yet understand. Is why does the digit arming mode result in much longer measurement times, 10, 100 times longer than the time arming, even if we finally end up with having the same amount of digits there? I can't find anything in the documentation that would explain that these modes should be more or less equivalent if I look at all the other information that I can find in terms of accuracy and otherwise. So I'm really not getting there. So better understanding what the difference between these modes are, that would appreciate. And there's this other issue I'm having here with the channel indicator lights and the way that they flash and represent the incoming signal. I don't understand that at all either, and the manual doesn't say too much about that, and probably going to make another short episode about that because I think we've been talking long enough already. But I hope this was useful information to you. I really love my counter, and I would I encourage people, if they have similar type of needs as I had, to consider getting a second-hand meter on the net. It's better for the environment as well, and it's a very satisfying instrument. So with that, this is the end of the episode. I hope you enjoyed it. Do like my channel, that helps, and hope to see you for the next episode.